So while Giuseppe gets set up, let me introduce Giuseppe as our speaker who's going to open our symposium part of our school. Giuseppe is faculty at EPFL. Before EPFL, he was at Flatiron Institute, Simons Foundation. Many of us who are having fun using machine learning have been introduced to the idea from Giuseppe's very famous paper, where he boldly claimed that maybe machine learning neural network architectures can be a good way of representing many-body quantum states. Since then, he's been keep pushing that frontier, also making the algorithms available for people to download and use. And we've been all learning a lot from him. So I'm really happy to have Giuseppe as our first speaker. With that, please take away, Giuseppe.
Hi, thank you very much, Eun-Ah, for your very nice introduction, and especially for taking care of organizing this work. I mean, this symposium at school. I mean, I see that there is a lot of technical details to be ironed out, and it's very nice that you managed to do that also with your collaborators, of course. So I'm honored to be the first speaker today. And I will give you an overview and also somehow a report of our recent progress in the program that Eun-Ah was just mentioning, which is about learning, if you want, many-body quantum wave function, and with these machine learning approaches, study interacting quantum matter. So just to clarify. Maybe for the younger generation, what we want to do here. Essentially, we are interested in studying, broadly speaking, interacting quantum matter. So you can think of all sorts of problems in chemistry, material science, atomic physics, nuclear physics. So all domains of physics where you have, and chemistry where you have strong, possibly strong interactions among electrons, among other sort of particles you have. And you want to study all the properties, for example, the ground state properties, the dynamical properties, the thermal properties of this matter. Okay? But more broadly, we are also interested in understanding how we can, for example, harness these many-body phenomena to study, for example, to build, for example, quantum computers. So to harness entanglement and many-body effects to build new simulators, for example, of quantum matter. And in all of these problems, being able to solve the basic building blocks of quantum many-body physics is really fundamental in trying to advance our understanding of a lot of interesting open problems. Now, the main mathematical problem, if you want, that you have to solve there, for example, if you try to solve the famous time-independent Schrödinger equation, so you have a Hamiltonian, you have a wave function, psi n, a set of wave functions that are the eigenstates of the Hamiltonian, as you know, is that in general, diagonalizing, if you want, many-body Hamiltonian, quantum Hamiltonian, is an exponentially hard task. Okay? So why is it exponential? Because, as you know, the size of this vector, if you want, of this wave function, is exponentially large in the number of particles that you have, in the number of spins or qubits, if you have a qubit Hamiltonian. And even though the Hamiltonian as a matrix, for example, if you look at system of discrete particles or spins or qubits, even though this matrix typically has a very special structure. So for example, we know that for Hamiltonians that describe physical systems, they are so-called, they satisfy this k-locality property typically, so which means that each of the rows of this matrix are sparse, in the sense that you only have polynomially many entries. So this is a very special property of these physical Hamiltonians. However, despite that, still this, if you want, the linear size of this, or the total number of non-zero matrix elements is very large. So we cannot use, advanced techniques to diagonalize this beyond what we can store in current hardware. What I plot here, as a function of time, is essentially our ability to store in hardware, if you want, wave function, quantum wave functions. And you can see that our ability of storing wave functions in the past 5,000 years has not improved dramatically if you look at this into perspective, because if you consider the problem of storing, if you want, wave functions on piece of papers, you can store there around 15 qubits if you write by hand all the coefficients of your wave function if you want. And nowadays we can do maybe 54 qubits or so. And really the limit there is the amount of information that we can store in even the most advanced digital hardware. For example, this is the largest supercomputer, one of the largest supercomputers we have nowadays. So there is an exponentially large barrier, exponentially stiff barrier that really does not allow us to solve exactly, again, I stress here, exactly the most general Schrödinger equation for many particles. Okay? So we have to stop around 50 particles or so. However, I mean, we are physicists, we like challenges, we like finding solutions to or approximations, if you want, to very hard problems. And that's what I'm going to tell you about today. So that's the core, if you want, of the methodology that I'm going to discuss today. And the core of this methodology are variational representations. Okay? So the main idea of these variational representations, of the variational method, if you want, which is as old as, I would say, quantum mechanics, so it's a very old idea in the field, is that, I mean, there's this notion that in general, as physicists, as chemists, if you want, we are interested in very specific states, right? So we are not interested in the most general quantum states that in general you can picture living in this large Hilbert space, so this outer box here. But instead, we are interested only in describing this smaller subset of states, these physical states, right? Which are, as again, very special states in the sense that they are solutions of the equations, founding equations of quantum mechanics. So the Schrödinger equation, time-dependent Schrödinger equation, Lindblad master equation if you have an open system. So all of these are very special states that are somehow not, random, if you want, states in this space. So the hope here, the hope of the variational method is that by suitably writing a parameterization of, if you want, many body wave functions, we can try to go there and try to span this subset of physically relevant states as much as possible, okay? So in the following, what I will do is that I will consider variational representations of many body wave functions that in practice, I mean, to be really specific, if you look, for example, at a generic many body state of n qubits, or n spin 1/2 particles, as you can see here. So you see that in general, I have 2 to the n basis vectors that are these guys, okay? So what I will do is that I will write a variational representation in which these coefficients, so the amplitudes, if you want, of the wave function in this computational basis, are parameterized by a possibly large set of weights W, set of parameters W. And in general, so the hope is that by changing these parameters, there can be millions or one, depending on your taste, you can try to span this subset of physical states as much as possible. Okay? So this is the key of this variational idea, which is a very powerful idea in many contexts in chemistry, physics, etc. So as Eun-Ah was mentioning, if you have questions, you should definitely ask them at any point in time. I'm very happy to take them also during my talk. So this is the basic of variational representations. Then, of course, the main problem is how do we pick these variational representations? So I would say that traditionally there has been a very successful way of picking variational states, which is what I would call special purpose variational states. So these typically are physics-inspired many-body variational states that have been...
Giuseppe,
yeah.
There is a question in the chat. Is your physical states including not just the ground state wave function, but the excited states violating area law?
Yes, that's a good point. Yes, so I'm including all states that satisfy even the time-dependent Schrödinger equation or even a high temperature state. So in general, yes, you can have volume law states and all sort of states that break. Yeah, that's a good question. So what I was mentioning here is that historically, let's say, people have focused on, prominent people. All of these guys essentially are Nobel Prizes, as far as I know, or almost all of them, have focused on devising essentially wave functions that are suitable to solve specific problems. Okay? So for example, if you consider the case of BCS wave functions, so these have been introduced to explain the phenomenon of pairing in superconductivity. So these are really specific functions, if you want, wave functions. But these have been very successful in describing, for example, again, these Hamiltonian that correspond to superconducting states of matter, right? There have been other wave functions, Laflin state used to describe, topological phases of matter, Variational 1D system typically, Jastrow states, superfluid, etc. But however, all of these are special purpose. That's what I try to depict here, in the sense that you pick a specific point in this space of physical states, right? So you span a small, precise, extremely useful, but small area of quantum states. Okay? Because here, for example, you only have the ground state of a specific Hamiltonian, for example. However, I mean, in the 90s, there's been an absolutely, if you want, dramatic change in paradigm or in the way we approach, if you want, variational wave functions, which is due to Steve White, essentially, to the introduction of a family of wave functions that do not span, if you want, point-wise entries in this space of physical states, but rather, manifolds of larger regions of states. So this is the fundamental idea, if you want, of matrix product states. I'm sure you've heard about this. So in essence, you have that your amplitudes are written as a product of matrices, a trace of product of matrices. And you can show that these states, for example, are exact or essentially exact when you try to describe low entangled states in one dimension. Okay? And again, by changing, for example, the size of these matrices, you can span larger and larger portions of your physical states. And in practice, you can span really a very large fraction of the interesting physics in 1D. Another general purpose, if you want, family of wave functions that can be used, again, beyond one single point as the standard, if you want, physics-inspired approaches, that is very popular these days, are parameterized quantum circuits. Okay? So I'm sure you've heard about quantum computing, quantum circuits. And in this case, the idea is that you have unitaries that are parameterized. So again, they can have a lot of parameters that here I denote as theta. And again, you can try to essentially tuning these parameters, prepare an arbitrary quantum state that is generated by these unitaries. Okay? So and again, if you choose your unitaries in a nice way, you can span larger portions of your space of physical states. These have an advantage because they don't have this storage problem that you have, for example, in the classical methods, for example, like these tensor networks or matrix product states. However, they have other drawbacks. So, for example, they can only approximately realize this digital quantum computing paradigm because typically on at least current hardware, you have noise. So at the end, the kind of states that you can prepare are limited. In some cases, strongly limited even by the amount of noise that you have in your system. But I wanted to mention that this is one of the latest, if you want, ways of parameterizing quantum states. And in general, I mean, this was actually one of the questions that was asked before. By using this combination, if you want, of different wave functions, we know how to span, sometimes in theory, sometimes in practice, several parts of this area of physical states. So I was mentioning that, for example, matrix product states or their generalization in 2 dimensions can typically describe pretty well area law states, even though there are some area law states that are not efficiently described, especially in 2 dimensions by PEPs, for example, without entering too much into the details. But there's a strong overlap between area law states and the tensor networks that are this yellow region here. There's a strong overlap, of course, between if you want, physical states and what you can generate with a parameterized quantum circuit, okay? But again, even if you have a fully error-corrected quantum computer, you cannot generate the whole set of physical states, okay? In the sense that you cannot prepare, in general, in polynomial time, the ground state of a given Hamiltonian, for example. So, we really need to have a combination of these techniques in order to try to span as much as possible this space of physical states. Okay. Now, what can we do about that? How can we try to span even more, or span other parts of this region that those that are currently accessible? So this is the idea of using neural networks. So if you want using representations that are inspired by ideas in machine learning that you will see more in detail, I guess, during this school. But let me first introduce what I mean by neural network quantum states. So this is a parameterization that we introduce in this paper, and essentially what you do is that you have a neural network that is depicted here. So this is a famous convolutional neural network, for example. And essentially, I mean, mathematically, the expression for the coefficients that you have of your wave function are parameterized in this case by this expression here. This is a compact way, if you want, of writing a neural network of L layers here. And you see that essentially the input of this network Z will be my quantum numbers. So this is a vector of quantum numbers, for example, plus or minus 1 if I have spin 1/2 particles, or 0, 1 if I have qubits. And you apply to this vector a linear transformation of characterized by some weights W. And then you apply component-wise a nonlinearity. So this G is typically a nonlinear function. And you repeat this operation many times, a cascade of linear and nonlinear transformations until you reach the last layer L, which in this case will have just one output that corresponds to the complex valued amplitude of my variational, of my many-body state. And you see that here this is variational because the weights W here and also the choice of the architecture will intrinsically determine the manifold, if you want, of states that I can span with my representation. Okay. Now, what can we do? I mean, why these representations make sense? I mean, there are some mathematical reasons that I would like to highlight here, and there are also some more physical reasons. So the general mathematical reason is that it is known that if you have a nonlinear function, so a composition of two nonlinear functions, such as this one, so phi and capital Phi are two nonlinear functions in this theorem, proven by Kolmogorov and Arnold, you can show that in general you can represent an arbitrary high-dimensional function. Okay, so why not also the many-body wave function? So if I know that I can represent an arbitrary n-dimensional function using composition of nonlinearities, this means that in general I can also represent high-dimensional functions that are relevant for physics, for example, but not limited to many-body wave functions. So this is what people call universal approximation theorems. So the fact that we can find a network that in principle approximates my wave function. Then there are also more physics, if you want, motivated reasons why we want to use, for example, neural networks, deep neural networks. And the main idea is that if you have a deep neural networks, for example, like such as the one with L layers that are depicted here, you can show that you can encode efficiently, for example, volume law entanglement. So this has to be contrasted with the, for example, planar tensor networks that typically cannot do that efficiently. This points to the fact that, for example, if you have a very highly entangled state, typically with volume law entanglement, it might be advantageous to try to describe it using a neural network, because again, it's conveniently encoded with a polynomially sized deep network. This is what is being proven in these two papers, and many others. More recently, actually, we've established a couple of months ago a direct connection, if you want, between these two languages, these variational languages of describing many-body states. So on one hand, if you want tensor networks, so if you want a description of many-body states based on contractions of tensors, and this new, if you want, way of parameterizing many-body quantum states based on neural networks. So it turns out that there is a direct one-to-one connection. For example, if you take a generic matrix product states, so for those of you who've seen this, they will immediately realize that this is an MPS, so a matrix product states like the one that I was describing before. You can show that this can be always efficiently written as a small, I mean, polynomially small or large neural network, whose depth is only logarithmic in the sides of the system. Okay, so this is the result of this mathematical theorem. But this is just to say that we have ways of converting, for example, among representations. Okay? And this is general for arbitrary, if you want, tensor networks you can contract on a classical computer. So this has allowed us also recently to establish somehow a kind of representability diagram. So again, how large are these regions of quantum states that we can try to represent using these variational states. And you can see that essentially, if you consider neural network quantum states, which are these, if you want, red area here, this whole blob here. So you can show, this is a consequence, if you want, of the theorem that I was showing you before, that if you have a polynomially sized neural network, you can describe, for example, exactly the ground state of gapped 1D Hamiltonians. You can describe all Merrick's product states, and you can describe all PEPs that you can work with efficiently, if you want, on a classical computer. Then, I mean, there is some region to spare here, which are essentially, for example, all those voluminous states that are not typically efficiently described by a tensor network, for example, with a small bond image. Okay? So these are those voluminous states that I was describing before. So this is the state of the situation at the moment. I notice that I didn't put on this diagram parameterized quantum circuits, because I would argue that in that case, the situation is less clear. I mean, at least some of the boundaries are less well understood. Now, let's go to the practical application, if you want, of these parameterizations. I mean, now we've seen what kind of states we can try to parameterize. So the main applications, one of the main applications is learning ground states. Okay, so I'm given a Hamiltonian, your chemistry, your condensed matter Hamiltonians describing electrons, protons, whatever. You want to find an approximation of the ground state of this Hamiltonian. Okay, so what you do is that you resort to the famous variational principle. So you try to minimize the expectation value of the Hamiltonian, and you hope typically that by minimizing the energy, you will get a good approximation also of the ground state. Now, the key point is that this expectation value can be rewritten as a statistical expectation value. This point was realized already in the 60s by Macmillan. And I'm not going too much into the detail, but you can show that you can evaluate for an arbitrary neural network. There's a good heuristic to evaluate, if you want, expectation value of the Hamiltonians using Markov chain Monte Carlo. Now, one example application which has been very popular and on which several groups have worked, and that's why I want to point it also here as a very interesting benchmark, if you for this kind of techniques, are spin models. So again, now I'm considering two-dimensional spin models. So I'm now on a square lattice. I imagine that I have on each of the edges of this, on each of the nodes, if you want, of this square lattice, I have a spin 1 alpha. And this spin 1 alphas interact with, for example, an exchange interaction of the Heisenberg type, this J1 interaction, and also a J2 interaction along the diagonal of this square lattice. So this is the famous J1, J2 model, which essentially we don't know how to solve exactly with any existing technique. You know, tensor networks, quantum Monte Carlo, quantum computing. Essentially, with none of these techniques, you can solve this model exactly. Okay, so it's really, you know, I believe a good way of benchmarking also new techniques and existing approaches to try to see which one is getting a better, if you want, approximation of the ground state. And one physically open question here is, for example, if there exists a spin liquid phase that intervenes these two ordered phases that appear when J2, for example, is small, so this antiferromagnetic ordering, and when J2 is large, whereas you have this striped order. Okay. Now, in the Heisenberg limit, so when you have J2 equal to 0, so this is just the Heisenberg model that can be solved instead exactly with Monte Carlo, quantum Monte Carlo. So we have a good benchmark already for our models. There has been, I like to show this slide because it shows the progress that there's been in the field since our first paper until the latest applications. And what I'm showing here is the error that you make, for example, on a 10 by 10 cluster on the energy. And in the early applications that were based on these very simple-minded restricted Boltzmann machines that are just shallow neural networks, only one layer, essentially one hidden layer. The error you could get were around 10 to the minus 3 or so. Then by using deeper architectures, as we did in this work, with some convolutional filters, you can improve the accuracy. And even recently, as recent as last year, you can further improve the accuracy in 10 to the minus 5, which is essentially almost an exact solution for this model. So what I wanted to say here is that in the past 2 or 3 years, we've learned much more how to use even more complicated networks. So going from here to here, the structure of these neural networks has significantly increased. So here we had maybe 1,000 parameters, here we have 1 million. But in doing so, we also typically get a better understanding or a better knowledge, if you want, of the ground state, and we increase the accuracy of the approximations we can get. Now, this model, as I was mentioning, is very challenging. It's also very challenging for neural networks, especially in the region around when J2, so this interaction strength is around 0.5, which is the point of highest frustration. So in this, if you want, accuracy diagram that we showed in 2019, you can see these are the energy differences. So essentially, if these points are in this part of this diagram, it means that these neural network quantum states are more accurate than some existing approaches. Otherwise, they are worse, so they perform better than other approaches, for example, like the Emergence. And you can see that we were doing pretty well, I would say, already in this first work, but there was a very interesting and open problem, which is essentially improving the accuracy of how well we describe, for example, these strongly frustrated phase in the middle of this diagram. Okay. So why is it so? I mean, it has been argued, for example, in this very nice paper, that one of the reasons it is hard for a machine, if you want, for a neural network to learn these frustrated phases of matter, is that the number of samples that you need to see in order to understand, if you want, these strongly frustrated phases is much larger than the number of samples that you need if you want to try, for example, to learn instead these ordered phases. Okay. So you can think that if you want to learn this ordered phase, these two extremes, the number of samples, so how many snapshots of the wave function you need to see during your simulation, is much smaller than what you need to see in a disordered spin-liquid phase. This is shown for a very similar model, not exactly the same. And you can see, so this is the accuracy that you get. So the overlap one means that you have a very high accuracy. And you can see that there is essentially a sort of very interesting phase transition in the number of, so this axis is proportional to the number of samples that you need to process. And you can see that at some point you reach accuracy 1, but there's a critical, if you want, number of samples that you need to see. And you also see that this critical number of samples moves away when you increase the frustration in the system. So this means that the main limitation, as far as we understand, of these neural network approaches is really the amount of samples, the amount of experiments, if you wanted to perform in your training in order to see, in order to find better approximations of the ground state. However, maybe there's a question, yeah? Yeah, okay, otherwise I can continue. Yeah. Okay, yeah, no problem. I mean, otherwise I can just continue and you can ask the question later. But what I wanted to mention is that recently there's been always, you know, this is a very dynamically moving field where there's improvements essentially, I wouldn't say every day, but almost. And for example, if you look at this recent paper, the second version of this paper, actually, not even the first that was originally published in 2020, the second one that was published a few months or maybe a month ago, essentially, even at this very challenging point of 0.5 and using a shallow neural network, so an RBM, but with some symmetry tricks that if you want, you can read in here. It has been shown that you can really, as you can see, you can improve again systematically on the existing state of the art, and you can go essentially now at a point where these neural network approaches have the best energies, as we know, on this model, on this very challenging model. So you can see that, already at this point, by working a lot on these neural network architectures, on the symmetry, for example, this is a point I will do in the following. It has been shown that we can indeed try to advance the current state of the art in terms of wave function that are useful to describe, for example, strongly interacting magnets. Okay. Now, so if there are no question, maybe I will move to the second part of my talk. And in the second part of my talk, I will try to address, if you want, the original promise that I made you at the beginning, so that we want to study, for example, problems in chemistry or in materials where you have fermions, right? So we know that most of the interesting matter, if you want, around us, at least at the energy scales that we can experience, is made out of fermions. So until now, I've talked only about spins. So the question is, how can we describe spins or fermions beyond what we've done already for spins?
Giuseppe, I think there are two questions.
Yes.
Sayed Al-Reza, can you unmute yourself and ask question?
I have one question. Can you use any of these neural network methods to determine the critical exponents, for example, at the phase transition?
Yes, so you can think of this as a black box, if you want, for trying to find an approximation of our ground state. So once you have your observables, you can do all sorts of critical scaling that you would do in an experiment, in an actual experiment, or with other approaches. So in principle, yes. So if you have a correlation function, you just measure that correlation function, and then you can scale that to a larger system, and you can pinpoint the transition. I will show you an example of that later. Maybe there was another question, but maybe it's already gone. So I guess I will go on if you don't mind.
I think you can go on. Yeah.
Yeah. Okay. Thank you. So the promise of doing fermions, the original issue we were discussing. So there are many ways of doing fermions with neural network states. I will discuss one that we introduced last year or so in collaboration with Antonio Mezzacabo at IBM and Kenny Chu at the University of Zurich. This is if you want, a simple-minded way of doing it, but in some cases quite effective. So the idea is that you can map fermions to spins. Okay, so this is in some cases a very well-known approach in condensed matter. So the famous Jordan-Wigner mapping is exactly a way of mapping, if you want, fermions to spins. I will discuss this in a second. But then there are also other mappings that can be done. So the Jordan-Wigner is not the only one you can do. And for example, in this work, we explored also other possibilities. So this Bravik-Hidayet mapping is also another way of mapping fermions to spin that is very popular in the field of quantum computing. So for example, the Jordan-Wigner mapping, which I guess is very famous in condensed matter, essentially allows amounts to representing, for example, fermionic operators, CNC dagger, in terms of spin raising and lowering operators, mediated, or if you want, with the addition of these strings of sigma z that carry the sign, so, right? So essentially, because when you exchange to fermions, you want that you have the anti-convolution relations, and this is taken into account by the string of interactions sigma z that take into account the sign. Okay. So if you have a generic, if you want, fermionic Hamiltonian, you can then map it through this very simple mapping into a spin Hamiltonian that is in general the sum of products of Pauli operators. This is what this capital sigma is. And in general, this mapping is universal in the sense that an arbitrary fermionic Hamiltonian can be written in this term. One of the drawbacks of this is that this string of operators can be very large, so typically extensive in the system size. But there are ways around this problem. One way around that I'm not going to discuss into details, but that is very interesting and typically much less known in condensed matter, is through this Bravik-Hidayet mapping. So the idea here is that you map, again, these CNC dagger operators into a linear combination of dressed, if you want, sigma x operators, but where these A operators now only have a support on a number of spins that is typically logarithmic in the number of fermions, instead of being linear in the number of fermions as it was in the previous case. So the advantage of doing so is that the spin Hamiltonian that you get out of this mapping is typically more local, in the sense that you don't have this super long range interaction involving n-body as you have, for example, in the Jordan-Wigner mapping. Now, just to give an example, then what we can do is that we have our chemistry Hamiltonian from first principle. So what we do is that we have a basis set, we discretize our Hamiltonian on this basis set. For example, you can see here a couple of molecules, C2 and 2. These are the dissociation curves. So in essence, the energy when you pull apart these atoms, these diatomic molecules. And you can see that, again, using a very simple RBM, in this case, you can get pretty accurate results for these dissociation curves. So these FCI are the exact results that you can get on this basis set. And you can see that we are pretty close to the exact results here. And you can also see that this is the case also for more challenging molecules. For example, N2 is known to be more challenging for other methods, where you can substantially improve upon R3-Foc, which is this blue line, so the mean field if you want, but also improve, for example, at large distances to other approaches, for example, couple cluster, where they have historically some issues in this more strongly correlated regime, which happens at large distances. Again, you can ask yourself, for example, what happens if you have if you change the mapping. So, for example, if instead of using the Jordan-Wigner, you can try to use this gravity type. Well, it turns out a bit, if you want, annoyingly, that there isn't too much difference. So we were hoping in finding an improvement in using these more advanced mappings. Actually, even in some cases, these old school mappings like the Jordan-Wigner is more precise. I mean, as you can see in N2, these are the energies, so the lower the better. You can see that at parity of neural networks, in some cases, this Jordan-Wigner mapping gives rise to an easier to learn apparently representation of the wave function than this gravity type. But again, this is a special case. We don't know if this conclusion will hold also for other generic Hamiltonians. So this is left open. I just want to mention that this line of research, so the idea of using neural networks to study molecules, so to study chemistry, is extremely active these days. It started, I would say, with this backflow approach in 2018, and has been become really popular with thanks to these two papers. One in DeepMind London, so this part of Google that is working on deep learning. So this is this paper in 2020, and also this work in the group of Frank Noé that was using a similar approach. And the idea is that instead of working again in a discretized set of orbitals, as we do when we work with spins intrinsically, you can work directly in the continuous space. So that's what they do in these papers. And here the idea is that you consider what are called the neural network backflows, so which are modifications of your single particle orbitals. So you can think of, for example, of having an orbital phi that is labeled by momentum and spin. And you modify these single particle orbitals with a many-body function that depends on all the other particle coordinates, and that is parameterized with a neural network. So you see here there's some difference. We are not parameterizing directly the full wave function as we do on the lattice, but we parameterize this backflow transformation. And very recently in this very nice paper, so they've shown, as far as I know, that with this approach, which is called Fermionic with some extensions, you can really get state of the art on these results, on this energy, on these molecules that you can see here, and even compared with experiments. I believe that this is a very exciting area in which we will see a lot of more developments in the future, where we will be able to assess also much larger molecules than that can be done at this point in time. One application that is also in this spirit, even though not in the case of chemistry, but in the case of continuous variables, if you want. So if you want matter that is intrinsically continuous, so not on a lattice like we were doing at the beginning, is what we did, for example, recently in collaboration with people at Argonne. this is a work where we studied, if you want, the same, we used the same family of wave functions, so in continuous space, parameterized by neural networks, in order to study another problem, which is quite relevant in the context of many body problems, which is the problem of nuclear matter. So, for example, if you consider the nucleus of helium-4, okay, so which is depicted here. So essentially, you have strong interactions among these nuclear matter, and you have to solve effectively for actually much more complicated than high energy, the lower energy. Typically, Schrödinger equation we solve, for example, in the context of condensed matter, but it is possible to write effective Hamiltonians, for example, like these three-body effective Hamiltonians. And again, this is the beauty, I believe, of machine learning. You can use exactly all the technology we've used for spins, for chemistry, for condensed matter, and you can apply it almost as it is to a very seemingly completely different problem in nuclear matter. And again, with this, if you want universal machinery, or more or less universally, you can also, in this case, find a good approximation, in this case, of the wave function of this nuclear matter of helium-4. Okay, so for example, you can see here, this is the prediction of you can see that the energy scales here are, femtometers, so these are really high energy things. You can see this is the density profile for this nuclei, and you can see it compares well to other approaches you can do for helium-4. And again, this is the beauty, I stress it once more, of neural network approaches. This is entirely portable. So once you have this method working on a given Hamiltonian, you can relatively easily also make it work with a completely different physical system. With some, if you still need some physical intuition, but typically that's much less effort, if you want, than devising these traditionally hard, if you want, wave functions, traditionally physics-inspired wave functions. Now, since I believe that my time is slightly short, maybe I will just flash this application, which is about studying spinless fermions. So this is a model in, so Eun-Ah, can you confirm that I only have 5 minutes? Sorry, I can't hear you.
You have 5 minutes.
Okay,
yeah.
yes. So maybe I will skip this application because it's somehow related to what I was discussing before. I will just flash you to this paper where we study these spinless fermions. But I really wanted to tell you instead about this other project, which is going to be presented also, I believe, by a poster during this conference, which is about simulating quantum circuits. Okay. So I've told you at the beginning that among the most popular ways of parameterizing variational states these days, we have quantum computers. So quantum computers are, if you want, a way to parameterize highly expressive quantum states. So a way to try to understand if classical computing, if you want, is more powerful or less powerful in practice, not in theory, than quantum computing. It's important, for example, to understand how far we can go in simulating a quantum computer using a classical approach. Okay, so and this is what I would like to discuss here. So the problem of simulating classically with a neural network a quantum circuit. So in general, when you want to simulate a quantum circuit, then what you're after is essentially, first of all, a quantum circuit, which is an ensemble of elementary gates. For example, here I'm considering these 3 elementary gates. So the Hadamard gate, this unitary gate, this control Z gate, and this RZ gate. Okay, and one interesting aspect is that that we showed already in this paper is that you can, if you apply 2 of these gates on a neural network. So, for example, if you consider a very simple RBM again, you can apply exactly these gates on these neural networks. So, what does it mean exactly? It means that if I have this unitary, I can apply it to a neural network and get out of, after the application of this unitary, another neural network which has almost the same form as the input one. So this means that I can perform this operation efficiently, classically. Okay. The other thing that we can do is applying controlled Z gates. So this can be arbitrarily far apart entangling gates. So these two qubits can be even very far apart. And again, you can show that this can be applied exactly. So there's no approximation when you apply these family of gates. The gate that requires approximation, I mean, otherwise we would be able to simulate exactly all quantum computing, is the Hadamard gate. This is a superposition gate. And it turns out that if you apply it onto an RBM, for example, or more broadly onto a neural network state, you can only try to approximate the action of this gate with another neural network. You cannot capture this guy exactly. Okay, so and this is the core of our variational approximation this time. So in the previous case, our variational approximation was the problem of minimizing the energy, whereas in this application, our variational approximation is minimizing the infidelity. So what does it mean? It means that if I have my initial state, which is a neural network, and I apply the Hadamard on it, I would like to represent this final state phi as close as possible with another network with some different parameters theta prime. Okay, so and in order to characterize how close these two states are, I will define a cost function, which is the infidelity between these two states. So by minimizing infidelity, and I can assure you that this can be done with good heuristics efficiently using Monte Carlo, then I can find a good, possibly good approximation of my state after the application of the Hadamard. And then I can apply again and again other gates as I need them while running my quantum circuit. Okay. Now, an interesting point, which has been discussed also in another paper based on tensor networks this time, is that you can compare the noise that you have on the quantum hardware. So as I was mentioning at the beginning, when you run on a quantum hardware circuit, you are not running the exact circuit, but you're running an approximation of the circuit because you have noise on the quantum hardware. With the noise that you have, if you want, when approximating this state with a neural network. Okay, so we have some source of infidelity in the classical world that counts because this state is not exactly phi. Okay, so because I have a neural network, but on the quantum hardware, the source of infidelity, even when I apply the Hadamard, is given by the noise. So I have one noise which is on the hardware and one noise which is in the variational representations. So we can try to compare the two to see, for example, how small should be the noise on the hardware to beat, so to speak, the classical representation. So it turns out that if you consider, for example, relatively simple circuits, for example, like QFT, quantum Fourier transforms, the amount of noise that you need on the quantum hardware is relatively small, for example, of the order of 10 to the minus 3. This is if you compare with very simple RBMs, so again, very simple neural networks. I suspect that if you go to more complicated deep networks, the effective amount of noise that you would need to achieve on the hardware would be even smaller. Okay? So that's why beating classical computing at this point is hard. I mean, it will be done eventually, but it's not already done, I would argue, for physically relevant systems. Now, in this paper that we did with Matija Medivovic, who's going to present it also during his poster, so if you have questions, you can go to him. We simulated a circuit, the apparently complicated circuit that you can see here. So this is a QoA, so it's a family of quantum circuits that are very popular and have been also run by Google on their hardware recently. And they have an alternation essentially of this single qubit rotation, these Rx gates, so these gates here, and these 2 qubit interacting gates that are these gates here, okay? So what we do is that you can show that we can apply exactly these entangling gates here, but we need to approximate these rotations, sigma x rotation. Okay? So and essentially every time we hit one of these, we have to run this approximation procedure that I was somehow describing. So you can show that, for example, with this approach, using a few hours on a small, relatively small cluster, you can perform, you can simulate relatively large, I would say, circuits in this case. So, for example, Matija will tell you that we managed to simulate p equals 4. So p is the number of layers that you have in this architecture, in this circuit. Kind of QoA circuits with we believe with very accuracy. Again, for example, this is the cost function that we get for P=4. This is something that is not, as far as we know, implementable with the same accuracy on the hardware. Maybe it will be in the future. But again, you see that we have a way also to compare between classical and quantum computing using these highly entangled quantum states. And this is also the case where we really enjoying the fact that we have high entanglement, because, for example, if you wanted to simulate the same system using, for example, an MPS with a simple MPS approach, it would turn out that to get the same accuracy that we have in the cost function, you will need a bond dimension for this 54 qubits simulation that is very hard to achieve, for example, even on a high performance calculations using MPS. And again, this is because MPS are not done to do this kind of highly entangled circuits. And it's nice to see that instead, if you force your wave function to be more entangled, using a small number of parameters, maybe you can try to find a good approximation of your state. Okay, so this is my outlook. Sorry if I was a bit late here. As Eun-Ah also was saying at the beginning, we are pretty much committed also to making this software open source and available to a larger community. So for those of you who are new, I invite you to have a look at our project, which is called Netcat. And if you want, you can absolutely contribute to it and also use it even for your own research. It is based on JAX, which is developed by Google, based on XLA. This is by now, I would say, a pretty high performance package to simulate many body systems with neural networks. This is my final slide that I leave as actually as an open question. And the thing that I find particularly interesting these days, apart the study of fermions that I think it's extremely fascinating, is really understanding what are the limits in between, if you want, classical and quantum variational simulation. So if you want neural networks or met-exported states and other classical states, and the quantum states that you can run instead on a quantum computer, right? So understanding, I think, the limit where one, if you want, family of states ends and the other one starts, when there's an advantage in using these other family of states, I think is a very interesting open question that we can try to address, developing both sides of the story. So both the classical side and the quantum side as much as possible. Okay. So thank you, and I would be happy to take more questions.
All right. Well, thank you so much, Giuseppe, for a wonderful talk. At this point, we have 74 people in the Zoom, 28 people following through YouTube channel. So there's a lot of interest. There is a question from YouTube channel, somebody who's watching. This is Hai Feng Lang. I think he's staying there because I promised that I will ask the question for him or her. So the question is, what is the scaling relations between parameter numbers and entanglement? Is it still exponential scaling?
Okay, yes. So this is a very good question. So the thing that I was showing in this theorem at the beginning, that was proven by, for example, in this paper or in this paper, is that you can show that there exist voluminous states, okay, that you can describe with polynomially many parameters in the neural network. So I give you some specific, again, not the most general voluminous state. I give you a fairly large family of voluminous states. Then this can be written with polynomially many parameters. Okay, so this is the statement. Of course, again, this is in this spirit. There will be voluminous states, for example, out here that you don't know, that you don't necessarily are able to, that you're not necessarily able to approximate with a generic, with a polynomially sized network. Okay. But the heuristic, is where, is that. Yes, these states exist. They are typically, for example, states that have a lot of disordered. disorder in their coefficients. So for example, you can imagine that you are generating a quantum state out of a random Hamiltonian or out of a random unitary. Let's say that you are Google. Then you can expect, it's very reasonable to expect, that these essentially random states are very hard to compress, if you want, down to a polynomially sized neural network, because they have not enough structure you can exploit in order to compress them. Okay, but my point, if you want, or my understanding of this thing is that in most cases these states are not necessarily, let's say, the most interesting for physical application, because typically these are, again, completely random states that don't have a special interest in physics.
Okay, there was another question earlier. Sayed asked, I think his microphone was having issues, a question. If you're using data generated by, let's say, quantum Monte Carlo, can machine learning, can you guarantee that machine learning method has more accurate results than what we gave it to learn?
Yes, yeah, I'm sorry, because I didn't enter into the technical, but very important discussion. Maybe this wasn't clear, but so here we don't have any data, okay? So this is in spirit closer to those applications of machine learning, like reinforcement learning, where you don't have data, but you only have a task to solve, okay? So for example, in reinforcement learning, your task is to drive a car, okay? But you don't necessarily have data that taught you how to drive the car. So you make experiments trying to not crash the car, and if you crash, you try to improve your strategy in driving the car, right? So here it's something similar, in the sense that our, if you want, our model is not driving the car, but are just the coefficients of the wave function, and our cost function is the energy. So we don't have any external data in this application for the wave function, but we find it self-consistently. So trying to improve, so playing against Schrödinger in a sense, trying to lower the energy at each iteration of this game.
Another question, I think from the YouTube channel, is, does it require some specific structure like GUE or GOE in the spectrum, I suppose?
Yes, so right, so this is yeah, this is interesting. I'm not sure that people have really studied this. I would say that if you have again a very highly disordered, if your state again comes from a scrambler, so let's say a Hamiltonian that is intrinsically chaotic, or some unit that is intrinsically chaotic, then the consideration that I was telling you before apply. So essentially, you don't have a special state in your structure in your state. Now, GOE versus this I don't know. I think it's a very interesting question, but yeah, I don't know. I don't know if there is a link between learnability and the statistics of the level. This is actually a very interesting question.
Okay, Chung-Eun-An, can you ask your question?
Oh, yes, thank you. My question was, earlier you showed us your paper that neural network states have greater representability than even tensor network states. And I was curious if the learnability also satisfies something similar. For example, you could have a neural network state that represents a tensor network state, but it is sort of in a, because you don't find global minimums when you do a variational approach. Can you well learn that state?
Right. So generally speaking, both training, so to speak, tensor networks and neural networks, I mean, they both belong to a family of NP-hard problems, essentially. Okay. So training these things is in principle is a nightmare in all cases, because these are hard optimization problems. Even for an MPS, for example, there's no. Yes. I mean, in general, there is no, unless you have a 1D Hamiltonian, I guess, but in general, you can, I think there's no proof that you can find the minimum of the absolute minimum of your functional. And the same is true for neural networks. Now, having said that, it's true that tensor networks, especially MPS, I would say, are typically much easier to optimize because they exploit locality. Okay? So in a sense, the fact that you have locality limits you in the fact that you can represent only, if you want, area states, but in some cases allows you to optimize things better, especially in 1D. This is true. So in general, yes. So we, again, as I was mentioning, doing the equivalent diagram for learnability, I think it wouldn't be very interesting because I think that in both cases it's hard. But in practice, especially in 1D, I would say that training an MPS can be much easier than training a neural network. Yes.
Okay. So far, the last question is, will you make the slides available? And I second that question. Can you email Jonathan the slides right away?
Sure, no problem. Yeah, I'll be happy to do that. Yeah. Okay. Yeah, so maybe I can also add some more technical details that I left out because for those of you who are interested in how to optimize this.
Okay. Any other questions? Okay. Sung-Shan Lin.
Hi, thanks. Thanks, Giuseppe, for the nice talk. Just curious about the final slides that you show about the MPS comparison to the NQS to simulate quantum circuits. So how is the MPS simulation, how is it done over there? Is it done in the way that like Stoudemire, they truncate it at each steps when you apply the gate, or you take the final state and learn it directly with MPS?
No, this is at each step. Yeah. So this is done really assuming that you don't know, because here we don't have the exact wave function, right? This is a 54 qubits. You cannot do it. You cannot learn it if you want with the MPS because we don't have the exact state. We have a neural network approximation, but we don't have in general the exact state. So here this is done really, applying a gate approximately variationally with the MPS. Yeah, here we use the code that is based on iTensor that Giacomo Torlai did. It's called PastaQ now, I remember. Yeah. But yes, you approximate the gate variationally. So yeah, of course, the advantage of the MPS is that you can apply exactly the Hadamard, but you have to approximate the action of these long-range entangling gates, right? So these are the differences between these two approaches. We have to approximate these Hadamard or this single qubit rotation that instead you can do exactly with the MPS, but we can do this exactly, and in the MPS you have to approximate this. So there's a reversed order of approximation.
Okay, are there any other questions? If not, let's thank Giuseppe again for a wonderful talk.
Thank you.
All right, let's see. So the next speaker is me. So let me share my screen. Let's see. Oh, not desktop. Oh, wait. Give me. No. All right. Okay. Now I have a window that I can share and share screen. All right. So I want to talk about machine learning of quantum emergence. But before I start talking, I want to ask you guys a question. Well, this whole symposium school is a big experiment, trying to do this all remotely. So keeping up with that adventure, I want to ask you guys, what comes to your mind when you think of machine learning? What comes to your mind? Like, why are you here? Can you just type it in whatever comes to your mind into the chat, please? I'm watching the chat. Okay, big data, large data sets, new tool to study physical systems, mathematical method, super smart black box, statistics, minimization. All right, great. Glorified fitting, I like that. Black box, optimization based on training data, non-interpretable. Okay. All right, cool. So, so that gives me some sense of like, what your exposure is. Giuseppe's talk focused on the approach from like, trying to use machine learning as a tool for computing, right? Computing, trying to find better wave functions, efficient representation of wave functions. I am going to approach it from the data perspective, and that's sort of my background because I've always been interested in trying to understand experiments and observations. And in old days, we call that phenomenology, and now we can call that sort of data scientific approach. So that's sort of the way, the angle from which I want to approach. So I will go over two specific projects, two specific papers that are highlighted here. But my interest in using machine learning has been the fact that there is ever increasing complexity and richness in data, experimental as well as synthetic or simulated data, with advancements in computing that now include new type of data from quantum simulators. And what we seek, me as a theorist, but physicists in general, we would like to gain understanding. And understanding really means gaining some theoretical insight, having a simple way to capture the gist of what is going on. And as the data becomes richer and more complex, and richness or complexity or volume, I all define in relative sense. So as the data becomes more complex compared to what we're used to thinking about 20 years ago, 30 years ago, trying to make that connection between data and theory becomes more challenging. But we think of, we want to understand the data and connect it to a theoretical insight, but we also want to use that understanding ultimately to make predictions. And as the information content in our condensed matter systems or quantum matter, because of the large Hilbert space, is enormous, ultimately, if we want to capture that information and understand, that capturing and understanding are two different steps. The community has really pushed the first part of these two steps, the capturing part. And we've really reached data revolution. For instance, tunneling density of states in 1960s, before many of us were born, were a macroscopic measurement where you take a single scalar quantity, single number that's tracked as a function of some single tuning parameter such as voltage. But now fast forward to today, we don't just measure one number, but we measure the tunneling density of state as a function of position. with subatomic scale resolution. So instead of one curve, you can have 10 million curves. And the challenge is, what can we do with that information that we successfully captured? X-ray diffraction in 1913. This is a screenshot from, this is captured from the original paper in the Proceedings of Royal Society by father and son Bragg and Bragg, where they, this is a main curve, main figure of their paper, where they presented the very first successful so-called forward modeling. That is, you do the X-ray scattering and you get these intensities going up and down as they change the angle, and they realized they can make an assumption that atoms form a plane, and incoming wave and outgoing wave interfere. And based on that assumption, with a tuning parameter that is the distance between the planes, they were able to fit the data and therefore extract the information. Now, today at synchrotron facilities, you don't detect 3 peaks, but you detect millions, tens of millions of peaks. And the question is, once again, what can we do with this? Probably all of you have heard about Stern-Gerlach experiments when you were learning quantum mechanics. And the Stern-Gerlach experiment was a very first projective measurement. By trying to interpret this splitting and how you can affect existence and absence of splitting by applying the fields in different orientation, Stern and Gerlach was able to reveal the existence of 2-dimensional Hilbert space associated with spin half particles and open up the new era of quantum mechanics. But fast forward to today, instead of looking at Hilbert space of single spin, we can look at the Hilbert space of 256 spins or more through projective measurements now of many more degrees of freedom. And what can we do with this kind of data? So the effort that we've been pushing in my group is to make use of the similarity between how we want to understand data and how the larger world looks at data problems. They, even outside of physics, even outside of science, people try to understand data that they have acquired, and they want to make predictions for the future. It's kind of innate in human intellectual quest. And understanding or compressing is called regression, and trying to make prediction is called generative modeling. So can we make use of the developments in machine learning world to assist or accelerate or go beyond what is possible? So this is a list of some of the exploration that my group have been pushing. Our very first successful example of using machine learning tools on real experimental data was this paper, where we used very simple neural network, single hidden layer, shallow neural network to gain insight from scanning tunneling microscopy data. We've also looked at projective measurements from IBM-Q. We've looked at resonant ultrasound spectroscopy. Spectroscopy is another problem with ill-defined conditions, inverse problem. And we've looked at non-Fermi liquid transport and from the simulated data of quantum criticality. Today, I will try to describe these 3 projects. One is looking at X-ray data, another looking at quantum gas microscopy and image-like data, and then non-Fermi liquid transport. But before I go further, I want to emphasize, I want to kind of communicate what's the kind of the principle that we found to be effective from the perspective of wanting to learn physics from data. So from this perspective of wanting to learn physics from data, we think of machine learning tools as tools. And here I'm showing a heavy duty blender, which is a wonderful tool for making smoothie or crushing ice. But if your task that you're after is not crushing ice, but if it is making guacamole, this simpler Stone Age tool can get you to the more ideal guacamole, defined by having little bits of individual flavors kind of blending and shining. And what's nice about this mortar and pestle, this very rough looking thing, is that you can see what's inside. Some of the participants in the chat window mentioned that machine learning is a black box and not interpretable. And sometimes, if you can just get to an end, perhaps that is enough. But if we are trying to use machine learning tools to answer scientific questions, I think, especially in physics, where we have a tradition of rigorous marriage between observation and math, we need to know what is going on. So then my message is that you have to pick your tools knowing your objective. You own the problem and you own the data, and you have to pick your tool based on your objective and try to keep it simple, because if you want to know why it works, to be confident that it is really working for a good reason. So let me start by talking about supervised machine learning on hypothesis testing quantum image data. So this is a problem of this, what to make of 10 million curves instead of one curve. And this was really pioneered. Really, lion's share of work was done by really brave and creative postdoc Frankie Zhang, who was then postdoc, now a faculty at Peking University, with an exciting group of his own. You can find more details of this work in this paper. This was sort of one of my very exciting collaborations with Seamus Davis. And the pre-processing that could really extract the right features was really pioneered by Andrea Mezaros at CNRS. So this is what the data looks like. This is STM data of enigmatic pseudogap state that has puzzled the community for a very long time. There are many aspects of pseudogap that are puzzling and mysterious still to this date. But if I just look at the STM data, this is what it looks like. And it's beautiful. It looks quite organized, and it looks almost like a piece of modern art. What do I mean by hypothesis testing? Often when experimentalists start a project, they have a question that they want to answer. Often they would like to get yes/no answer. Is this the right description of is this what is going on? There is a hypothesis, and they would like to get an answer between hypotheses. And it could be often very much like a multiple choice question. So for the pseudogap state, the question is, should we start from the momentum space or kinetic energy? We all know Hamiltonian has kinetic energy and interaction energy. And should we start from the kinetic energy? The position and momentum don't commute in the quantum world, so you have to kind of choose where you want to start your basis. If you start from kinetic energy and the Fermi surface it defines, the approach for understanding these patterns is to say, well, I have these flat portions of my Fermi surface, these flat portions, and the nesting is going to dictate what kind of periodicity I find. If you start from interaction, for instance, on-site Hubbard U, that's a strong coupling picture starting from position space. And you might say, well, at undoped system, I have parent compound has magnetic order, antiferromagnetic magnetic order. And if I start doping it, I will start introducing holes that also carry spin. This starting point invites you to think about physics that are commensurate with lattice. This starting point invites you to think about physics that are controlled by Fermi surface, which is not going to be commensurate by lattice. And it should evolve with doping. Now, the data looks like this if you blow up, and when you talk about periodicity, the first thing that you might want to do is Fourier transform. Unfortunately, if you Fourier transform this data, you have this kind of broad features. The fact that there is this feature showing up at within the Brillouin zone, this is the reciprocal lattice vector, is an indication that there is a visible structure. There is an observable structure present in the data. However, the features are really broad and very jagged. It's hard to know what's the leader, who's leading this pack of behavior. So we thought, well, perhaps we can try to recognize the leading theme, sort of the underlying hypothesis, like one can recognize handwritten digits. The trouble with trying to apply machine learning tools to quantum matter data is that often the data itself might be complex, and sometimes it can take up large volume or defined in a large dimensional space. But we don't often have equivalent or sort of same conditioned collection of data that can be used as a training set. So having scarcity of training set, which challenges trying to do machine learning. So what we did was to use what's a pretty common approach of using simulation, using sort of simplified models to simulate the training data. And here our simulation was guided by the model for various noise source, phase fluctuation, amplitude fluctuation, as well. And the phase fluctuation was taken into account in the form of smooth variation, as well as topological defects, and topological defects were very important. The idea is that we did not expect, and we tried just having a very loaded neural network, wanting it to learn everything by itself. And that was difficult to train. So we decided to make sure that we put in important features that are non-trivial in the training data. So the 4 choices that are going to they're going to be stand-in for hypothesis testing are different periodicities. Here, what we call, choice 1, choice 2, choice 3, choice 4, category 1, 2, 3, 4. And of these 4 choices, only one had commensurate periodicity underneath it, and then they were all disordered. And this is what the results look like as we add a particular underdoped state. As we change the energy scale from 66, 96 up, what we find is that the preference between 4 different categories. So what we do is we train that simple neural network with the training data, and then we give the real data. We give the real data in 2 orientations, X and Y, and we see what the network assessment judgment is. And what we found is that at low energies, different options were neck to neck in preference. But as you go to higher energies, above the pseudogap energy scale, we start to find the option number 2, category 2, to become really dominant. Give me just a second. Somebody's in the waiting room. Let's see if I can. Oh, Jonathan, are you around? Can you let someone in the waiting room? All right, so this is showing really the category 2 really takes off at the pseudogap energy scale. And now we walk along the doping range. This is a famous cuprate phase diagram. We're going to look at different dopings. And for this study, we've really analyzed the entire data set that Seamus's group have collected over a decade. As we walk along the whole doping range, we see that the preference for category 2, which is period 4 commensurate, modulation stays high until we approach sort of optimal doping, where the modulation becomes so broad and hard to detect. Looking at both the energy as an axis, looking at these full layers of data, and also studying this entire underdosed range of data, we discovered this robustness and universality, like robustness in how the category 2 or period 4 was preferred. And this was a pretty bold observation, and it required checking and benchmarking. We've looked at other data sets, and we've also looked at the topography to confirm that this preference of period 4 is not something that happens all the time. It was happening just for this underdosed set of data. So this was our way of arriving at the hypothesis testing result that this real space perspective of looking for period 4 was really the more sensible way to look at the data, just from the starting from the data perspective. But like several people mentioned, there is a question of what did the neural network learn? And we really wanted to answer what did the neural network learn? And we engaged in that effort on a different type of data set. Like Giuseppe mentioned, oftentimes if we identify similar type of problems, same sort of architecture, same sort of framework can be useful in physically very different type of data. So earlier I was looking at STM, which is image-like data. Now I'm going to look at quantum gas microscopy, which is a very different system. And now it is projective measurement. It's not sort of equilibrium measurement. Nevertheless, from the structure, the point of view of the structure of the data, it's also image-like data. This effort was led by my student Cole Miles, who is going to be a lead TA in one of the sessions. And we will be opening up this code that was used for this paper in that session. So projective measurements of today, quantum gas microscopy gives you this each snapshot. Each snapshot gives you this kind of image. And at a given state, you will have as many snapshots as you take. And the question is, from these snapshots, each are really the projection of the many-body state into one of those bases with non-zero weight. Can we reconstruct the state, or what can we learn about the state? Often a very effective way of looking at image-like data is convolutional neural network, which Kilian Weinberger is going to cover CNN in one of his lectures, starting from much simpler approach and taking you all the way to convolutional neural network and some of the principles that we used in this work, which was collaboration with Kilian. In convolutional neural network, what you do is you take your data and you apply a filter. And filter is one of those things that the network will learn. It's part of its parameterization. You choose the size of the filter, but you let the filter be learned. And once you have a learned filter, what happens to your data is that it gets convoluted. And that whole convoluted data goes through nonlinearity, sort of a firing, which leads to the output. Each of these steps have different meanings. The convolutional filter is going to be optimized to learn meaningful features. The nonlinearity is going to give us expressibility, because nonlinear function has infinitely many terms from polynomial perspective, so it can be much more expressible by having nonlinearity. But this nonlinearity, which gives us expressibility, is also what makes it hard to interpret, because it's hard to know what the filters actually did at the end. Even if we learn the filter, we can look at the filters. Cole's idea was to tame that nonlinearity so that we can understand what is going on. And the idea was that, well, instead of using the full nonlinearity, perhaps we can use a few orders of polynomial. It's still not linear. It's still somewhat expressible. So this is kind of a trade-off, optimization. We will give up on being as expressible as possible. And what we will gain is ability to figure out what's going on. And you can find out more about this work in this preprint, which is going to appear soon in Nature Communications. So let's see. So this is what's replacing the generic nonlinearity. We're just going to make powers of the convolution. And that allows us to interpret what each of the powers did. Specific scientific question, physics question we were after in this problem, in this paper, was trying to understand what is a better description of data. Similar to what we asked with the STM data, how should we think about the data? This is going to be Hubbard model at low doping, whole doped Hubbard model. And one way to think about the Hubbard model near half filling, which has antiferromagnetic order, is this idea of geometric string that Eugene and collaborators pioneered, where you think that at the time scale of hole's movement, the spin order of the surrounding state sort of frozen, and the hole moves by leaving a string of wrong bonds behind. Alternative perspective on a state of this whole doped state is so-called pi flux theory, which starts from resonating valence bonds and think of the holes breaking those valence bonds. The reason why we need to start from sort of state or wave function perspective is because the data itself is a projective measurement. So closest to the data is trying to understand what kind of many-body state could be underneath it. So we went through this analysis, and what allowed us to have the interpretability was this regularization path analysis, which is another thing that Killian is going to introduce in, I think, his either first or second lecture. So once we have trained correlation convolutional neural network, because these powers amount to sort of higher order correlation, what we did to figure out what the neural network learned, this is the interpretability question, was to fix the learned filters and do this regularization path analysis. In regularization path analysis, you put a loss function which penalizes using any of the inputs. This is the penalty for using inputs. So as you start to loosen up that penalty, the neural network is going to start using it wants to use minimal number of input information because there is this cost for using any input. And it will start using the input that is most informative, most characteristic, carries the most standing out features. And by looking at this regularization path analysis, which one is picking up, we realized, oh, it's the fourth order correlator of each of the filters, beta 104 and beta 204. And then we looked at, given my filter that was learned, what is a fourth order correlator? Well, so these were actually the filters that were learned, and this was associated with geometric string. This was associated with pi flux. Taking this filter and knowing the fact that it's fourth order, which means we want to look at 4 pixels combined from any of the 3 channels, we'll end up patterns like this. And then we realized, oh, you know what? I can see this pattern, this motif, in what we would have anticipated in a geometric string picture. This is sort of what would show up here. This is sort of what would show up here. So we gained confidence that what the CCNN learned was sort of in the same universe as what we would have thought. It's a sensible thing that it learned. And that was a great confirmation and exciting observation, because this can inform experimentalists to look for, say, fourth order correlation as a way of detecting this state. Now, with the limited time, I will just quickly flash our supervised machine learning on synthetic data, and then move on to unsupervised learning on X-ray data. So this was, I'm approaching this whole subject from, what is the data that I have that I want to understand, and what are the questions that I really want to answer, and how should I go about answering that question? So here, the target data problem is data obtained from Monte Carlo. And you might think that, well, if you can do Monte Carlo simulation because you don't have sign problem, what's the big deal? Well, when you can simulate something, does not mean you necessarily can naturally access what would be exciting from the experimental perspective. There is this disconnect between what can easily be measured in an experimental setting and what can easily be measured in a computational setting. And in this problem, we looked at trying to address a characteristic that's defined by transport property, that is non-Fermi liquid. And we are building on the advancements on sign problem-free models that allows us to access quantum criticality. So now we can finally simulate quantum criticality with fermions, but because what defines the phase, non-Fermi liquid, is defined by transport, which is not easily accessible to determinant quantum Monte Carlo, we are still left with that gap. So what we did in this paper was to study these two specific models without sign problem, which involves fermion doubling. And we used quantum loop topography as a feature selection, which was guided by the fact that we are interested in transport. And this is the result. So what's shown here is based on 3 training points: spin density wave, Fermi liquid, and non-Fermi liquid, nematic Fermi liquid and non-Fermi liquid. Data from 2 models were studied. And the color scale is a neural network outcome. And based on just these 3 training points, the neural network recognized these whole red fan region that very narrows down, funnels into critical points as a region that looks like this point in the phase diagram and very different from these points in the phase diagram. And this is obviously very similar to what we would have expected from analytical, sort of a theoretical expectations of quantum critical fan, and that was very exciting. And this was enabled by neural network being able to give us this sort of impression of the phase diagram rather quickly. So now, in remaining 10 minutes, I want to discuss yet another type of data, which is now, I think, of the 3 data problems that I mentioned, most naturally really big data problem. So this is unsupervised machine learning for voluminous X-ray data. This work was spearheaded by my former student, Jordan Vanderlee, and we had this adventure of working bringing people together from very different backgrounds. My colleagues at CHESS and Argonne National Lab, as well as my colleagues in computer science. And I think it was really the courage of young people who were willing to learn to speak, to people from different backgrounds made this possible. So what's the scientific problem that we're after? What you can learn from X-ray diffraction are different types of charge order and fluctuations. So in a fully symmetric state, if you have 2 atoms per unit cell in a 1D illustration, if this is your fully symmetric state, Charge density wave involves enlargement of the unit cell. So here we have a distortion, which enlarges the unit cell size from 1 orange atom to 2 orange atoms. And the way it manifests itself in X-ray is through the superlattice peaks. And the way the superlattice peak strength is changing from zone to zone reflects the structure factor, the form factor, that is what is inside the unit cell. That's the inside the unit cell and intra-unit cell information. Compared to the charge density wave, which increases the unit cell size and changes the periodicity, intra-unit cell order is harder to detect because it does not change the periodicity, therefore it does not introduce new peaks. So you have peaks at the same location. Now, the only thing that changed from the symmetric case peak, because if you're doing X-ray, you only have the lower side of the picture, you don't have the upper side of the picture. And you're trying to infer from this lower side what's going on in the upper side. So that's an inverse problem. What you find, the only difference between this state and this state from X-ray perspective is this slight change, which is showing what changed inside the unit cell, because unit cell size didn't change. It has to be just what's inside the unit cell, what's your unit that has changed. And that's reflected in how these peaks evolve from zone to zone. Even harder to detect are effects of fluctuation and structure in fluctuation. Here we're showing what is kind of the characteristic of fluctuating charge density wave. And it's going to give you these diffuse peaks. And the huge dynamic range between the Bragg peak and the diffuse peak can make this very challenging. So this large volume of data, what are we going to do? Probably not many of you are parents, but as a parent in pandemic, I faced a different type of embarrassment of riches. And this is like having a large box full of Lego. And I'm asked by my children to find that specific piece that they need for making the model that they want to make. And after doing this for less than a week, you quickly realize you don't want to look at the whole thing and pick one thing at a time and inspect manually. Similarly, you don't want to take the whole X-ray data and look at one peak at a time manually, because we get tired, because we cannot pay attention and our attention span is short in sort of a manual repetitive task like that. So a better thing to do, we quickly learned, was to sort. Maybe we'll sort by color, maybe we'll sort by shape. Okay, so that sounds like a reasonable approach. And it turns out sorting or classifying or sorting or clustering, grouping is kind of the basic of unsupervised learning approaches. With Lego, it was obvious what should be my sorting criteria. But what should be the sorting criteria for X-ray data if I'm interested in some emergent phenomena? So we realized that what we wanted to keep track of is how the data evolves as a function of a tuning parameter. Often we have a control knob, and very often the most important control knob is temperature. So let's look at the entire data set and let's see how it evolves as a function of temperature. And we treat each Q point in reciprocal space as a population, and we're going to track their kind of life history. Here, the lifetime is the temperature. Now, that's a great idea, but if you just look at the raw data and just plot it, and actually, I believe we were first to try to even plot like this. Most people don't think of plotting the entire data set as a function of temperature, because I guess it is anticipated it's going to be messy, and it is indeed messy. How are we going to approach this and find qualitatively different temperature evolutions? This was Killian's idea, who said, well, this sounds kind of like a speaker verification problem. You have a mix of voice signals, and you can learn that there are different characteristics, and you can separate different speakers. And another sort of machine learning idea that we imported from sort of cutting edge research in his group, Killian's group, was ideas from the label smoothing. When you have different sources of data, but you know that they are correlated, how to implement that to enhance your understanding of the problem here LiDAR and camera have the advantages and disadvantages, but if you combine them, you can get a better picture, more accurate picture of the machine vision. So we, in the meat of our approach is a very simple unsupervised learning model, a Gaussian mixture model. And what we did was to do the pre-processing of the temperature series so that we can deal with the scale, and we sort of remove noise. And then we assume that we try to find natural number of clusters and cluster using Gaussian mixture model. And through that clustering, what we learn is what is a characteristic mean behavior, mean temperature dependence, and what is the variance, and what is the likelihood of given data point, given Q point belonging to one or the other cluster. And this works, and this works really quickly. We can process terabytes of data in a matter of 10 or so minutes. Where we could really highlight the effectiveness of X-TEC, X-ray temperature clustering, was in studying parachlorocadmium renate. Cadmium renate is a parachlor metal, which has different structural phases, and it also superconducts at low enough temperatures. What's been puzzling is this large signal in specific heat, the signal being really large compared to very small displacements. Because displacements are so small, it's been hard to detect and be sure. Moreover, recent experiments on recent optical experiments, second harmonic generation, have raised questions on what's been a conventional wisdom about the nature of this phase. So my colleagues at Argonne National Lab set out to study this material in a really comprehensive way, so nothing is missed. That led to some 8 terabytes of data. So what one could really ask was, is this phase described by two-dimensional EU representation of the structure, which would have these two components, with this being slightly preferred state due to small anisotropy? If we want to ask that question, because this is a two-dimensional representation which would have Goldstone mode fluctuation, or in the presence of anisotropy, pseudo-Goldstone mode, finding Goldstone mode and connecting that with features in the structure would be a sure way to do it. But that was not something that's available with existing technology. So we give the data to X-TEC, and 10 minutes later, we find the trajectories that are obviously looking like order parameter. This is the mean trajectory. So out of that whole hugely varying data set, we can learn what is a mean trend. And moreover, we found that there is a selection rule. This was a surprising observation that was unknown before our work. Typically, this X-ray data set is selectively studied. People will look at a few peaks, even though the data is taken for a larger volume, because it's impossible to look at all of it. But with X-TEC, you can look at all of it, and we can discover trends. And this trend was really robust, and we could say it's robust because we looked at the entire data set. What we found was that there are these peaks, the green ones and the yellow ones, and they both turn on like order parameter near critical point, but in the phase, they have different temperature dependence. And the yellow one is kind of suppressed, as if there is something that's competing. And using this selection rule and the temperature dependence, we were able to infer that the actual distortion is I for bar M2. It's a particular structural group. But moreover, that cadmium and rheniums in the system are displaced out of phase by the same amount. And that was surprising because previously rhenium was not thought to be particularly engaged. And the fact that rhenium is very engaged brings in new possibility of importance of electrons, because rhenium has 5d electrons. Moreover, looking at the diffuse scattering data, we're looking inside each of the peaks. We found that the center of the peak, this little white region, little white dot, and the surrounding of the peak, which is diffuse region, behave differently, which we can blow up. So the diffuse region also showed sort of a selection rule by itself, with one of the group showing enhanced diffuse scattering throughout the phase 2, and the other showing enhanced scattering only below the phase 2, which made us question what could enhance diffuse scattering inside the entire phase, not only near at the critical point. And we thought of, oh, maybe that's Goldstone mode. And this is showing how the extracted diffuse trajectory compares against sort of a Landau model of the Goldstone mode, which shows that if you find the total diffuse intensity to be like this much is really dominated by Goldstone mode. So we credit all of this to Goldstone mode. And from that, we can confirm that the structure of the phase is I4 bar M2, and this was the first example of X-ray detection of Goldstone mode. So with that, I want to end my talk. I talked about applying machine learning to answer questions of quantum emergence from quantum matter data. And in terms of supervised learning, I talked about hypothesis testing between different theory ideas, which one better describe data, trying to learn about order parameter symmetry, or even non-trivial structure of the data. That imaginary time data of Monte Carlo must have the ingredients that are going to enter in telling us about transport, the real-time data. We just don't know how to extract it exactly, but there is a way to sort of get the sense of it. I have also talked about using unsupervised machine learning or sort of clustering approach to look at voluminous data in a comprehensive manner and learn the structure that is present in the data without any bias and going in. And I'm really excited to be able to share some of the inner workings as well as sort of logical thinking behind different approaches through our school. So I'm going to end now, and I'll take questions. Any questions? Cheng Shan Lin, how can I find you? Oh, there you are.
Yes, I'm muted already. Yeah. Thanks for the nice talk. I have a question regarding the supervised learning part about the hypothesis testing. So basically, I'm just asking that, have you think about another way of doing this by saying that we have these data, and at the same time, probably we can also have some classical wave functions. And I believe like a common way to do it in the machine learning community is that we compute the likelihood, like predicted by these different classical wave functions, predicting the data that you see from the experiments.
Right.
Comparing the likelihood, you know which one is the best wave functions.
Right. So in a way, this Gaussian mixture model is working. I didn't go into details, but let's see if I can move this. Okay. So here is the log likelihood, right? And we're trying to describe the actual data set. This I tilde Q is the actual data, and pi, that's the weight, and m, that's the mean, and s, that's the variance. And that's indeed sort of a classical probability distribution. And a specific form of probability distribution is a multivariate normal. So here we've assumed that this multivariate normal would be a reasonable way to capture data, which is a restrictive assumption. Specifically, it assumes every Q point behaves independently. So we kind of augment that assumption of independence between the Q points by including the label smoothing. But so that's the model, and we try to find the model parameters that best fit the data by maximizing the log likelihood. Does that answer your question? Cheng-Shan? Or
Sorry, I cannot unmute myself, so I cannot answer. So
okay.
That's actually not what I'm asking. I'm asking about the first part when you say
yes,
that
I understand. Right. Right. But now the difficulty is for the first part to come up with the wave functions for in some cases can be very difficult. And the actual wave function and the data may not be exactly overlapping, but nevertheless, they can describe the same phase. So if we're interested in the notion of phase, we chose to use the training set from one part in the phase diagram where we believe we have a good understanding. But in a way, the training set was generated based on sort of a simple picture, not exactly a probability distribution, but that's how we generated the training set. But if you have a specific idea, I'd be happy to discuss more later.
Yeah, maybe I could ask you afterwards. Thanks.
Yes, I'll be around during the coffee break. Timothy?
Yeah, Timo, thank you. Yeah, thanks. That was a really cool talk. I was really captured by this interpretability that you showed there. And I'm not quite sure if this is maybe too technical, but I was interested. I didn't really understand what the issue is with doing this kind of interpretability. So where the difference was between having the usual nonlinearity and having this kind of reduced nonlinearity.
Yes, very good. Okay, so here, so let's go to where we actually learn. Let's say we learn the filters, right? So initially we learn the filters and then we give a typical standard nonlinearity like ReLU. And we couldn't make sense out of why a specific filter was learned, because there must be some reason, but it wasn't clear to us. Because if you think of a nonlinear function made of this filter, it's very complicated. So it's hard to know exactly what aspect of this filter was really useful, even if we learned the filter. And that's a common issue that when people use CNN, run into. By doing CCNN, we had these specific powers, and each power enter as an input. And we are looking at when each of those inputs, each one of these are used. So that's beta. So now if you look at the regularization path analysis, you are not only seeing which filter is used, but you're seeing which power of given filter is used. So here we see a fourth order of filter 1 and fourth order of filter 1 and 2 were really important in getting up to like over 75% accuracy. And then you turn on the second order filter, and that brings us up in the accuracy a little bit. But other than fourth order and second order filters, like for instance, first order filter was not very useful. First order is actually just counting every pixel. So it's just the net density. Fourth order, the way we've constructed it means we have to look at 4 pixels at a time. So it tells us that take this filter, look at 4 pixels. It breaks down, CCNN breaks down the whole interpretation into very obvious and well-defined steps. So we look at, okay, this is the filter that we learned. Okay, I look at my path analysis. This is the order that is turns on the first. So now let me look at that filter collection. Now it becomes something that is very transparent. So that's what we found really helpful. Does that answer your question?
Yeah, thank you very much.
Sure. Any other questions? See, there is something in the chat window. Is there a general principle that limits the kind of data we can subject to this kind of learning, or in principle, is it possible with any experiment? Well, I haven't found the limit yet. I've been exploring a lot, as you can see. And actually, I personally find that to be the real fun of this. Now I can think about any sort of data, any experiment, even if I don't know how to get to the final answer all analytically, all by myself. I don't have to solve the whole problem all on my own. I think sort of interesting type of data that's very difficult to model are, for instance, driven systems or systems out of equilibrium, where going from the model, writing down model and figuring out what is a good methodology to go from the model to particular prediction, let's say time-dependent dynamics, when our abilities are not unlimited. It's a very difficult problem. And I used to stop, just not look at those problems altogether, because I would say, well, I don't know how I can be of help. So being able to get help from machine learning and sort of this data science approaches that help me bridge between what I know and the reality. I think of it as a bridge, and I think it could be used. It can be helpful in many different types of experiment. But generally, you don't want to beat the dead corpse, so there won't be much of a point in trying to use a newfangled approach to something that's otherwise easily doable. But if you encounter modeling problem, interpretation problem of your data, I think this is something that one should think about. Any other questions? All right, so let me just, after I just realized at the end of my talk, after the summary, there was something else. This is what I wanted to share. So, oh, Leon has a question. Who's Leon? Let me find Leon. Maybe hands are raised. Oh, yes.
Hi, can you hear me?
Yes.
Hi, yeah. Well, this was just going back to the question before last on your machine learning analysis of the Hubbard model. I was just wondering, so you mentioned that the algorithm converged on fourth order correlation functions. I was just wondering, how many higher order correlation functions after that did you permit?
Yes, very good question. So if you look at the archive posting and the supplementary of it, you'll see that we've explored, allowing up to, I think, 8 order, definitely far more than 4. And what we found in, this is empirical statement, is that, neural networks are often very lazy. If they can get something out of, 1 or 2 things, input, they really grab onto it. So for that particular problem of Hubbard model snapshots near half filling, like very underdoped, fourth order seemed to have been just enough. And we confirmed that by going up to higher order and seeing no meaningful improvements in performance after fourth order. Does that answer your question?
Oh yeah, absolutely. Thanks.
Okay, great. So these are my absolute last slide, and then we'll go to coffee break back in the Gather town. So picture here is Jacquard Loom. which was invented in 1800s, beginning of the industrial revolution era. Before the loom was invented, textile with pattern was something only really rich people could afford. That's why you can buy tapestry in museums of noble people. The jacquard loom made textiles with pattern available to a larger population. What was cool about this, what allowed patterning, was this. This is programmed. And the way jacquard loom was programmed was through using punch cards, as you can see through this punch card. So pattern is recorded into the punch card that gives the instruction, and the loom executes that pattern. Most people saw in this jacquard loom just a machine, a simple thing that does manual labor for human. What Ada Lovelace saw was the potential of taking this idea of giving instruction to a machine and letting it solve problems. And she envisioned using punch cards to program the computer. At the time, this was Babbage's analytical machine that she was thinking. And although that machine never materialized, we know in the course of history, punch cards were actually used to program computers. And so what I would like you to think about during the rest of the school is how can you take the abilities that these tools offer you and own it and rule over it and use it as a tool for advancing your scientific quest. And like these people, these are computers, human computers who could have been replaced by machine computer from Hidden Figures. They learned to program, so they weren't replaced. And so that's why you guys are here, I think. You're trying to learn to use new tools so that you can be on top of development. So on that note, thank you all for the wonderful discussions and participating. And I will see you